Hey class, I got a question, so I thought I'd make a video. It's actually from section 42.2, so it's a good question, but let me emphasize it is really not what you're asked to do. I asked you to do problems from 42.3 to get ready for the exam, and so this was a little bit outside of that scope, but it has something interesting, and somebody was asking about it, so I said, oh, why not make a video nonetheless? So keep that in mind, that it's kind of out of our scope of direction, and it wouldn't be on the test, and it's a pretty complicated one too. So all of those are that if you go ahead and watch this, just know that it's wouldn't be a good test question for, like, I'll point out for a couple reasons. But here's what it is good about, and so here's why I thought I would answer it with a video as well as, well, for that individual student, and then send it to all of you, and if anybody who wants to look at it, because we've been talking about in our class, you know, as we're wrapping up, we're doing this section on the introduction to quantum mechanics, and this gives me a chance to talk about it here. And I'll just read the question. It says, according to classical physics, a charge E moving with an acceleration A radiates at this rate. Show that the electron in a classical hydrogen atom spirals to the nucleus at this rate. And we've been looking at the reason for the need of quantum mechanics in our introduction. And the first thing we talked about was the photoelectric effect. So the photoelectric effect can only explain with quantum mechanics. And so we call that the birth of quantum mechanics. It was the first time it was Planck who came up with this idea of quantizing things. The second thing that came up then was, what did we do second? Einstein's photoelectric effect. And again, very interesting physics there that can only be explained if you quantize things. The third was the Compton effect. And the Compton effect, again, shows that we have to have quantum mechanics. The fourth one was the sharp spectral lines. And the fifth one was the instability of the atom. And that's what this is. And so this is a good problem showing that if you have an atom, its rate of change, the radius rate of change, follows this equation. And it's a negative, so that means it spirals inward. And so what I like about this problem, and the reason I decided to kind of pursue it and make a quick video here, was because here's what classical physics is saying. If you think of these things in terms of charged particles and not waves, then this electron would go around and it's accelerating. Now, according to electromagnetic theory, the rate of energy changed with time would depend upon the acceleration. And so something going in a circle definitely accelerates, so it would give off radiation and it would lose energy. As it loses energy, it would spiral in, and eventually the electron would hit the proton. And without quantum mechanics, the atom would spiral in and disappear. But I'm glad they have this part B, which it says, then ask yourself, how long would it take if we started at a radius that is 2 times 10 to the minus 10th, so roughly the size of an atom, about double the size of a hydrogen atom, and then it spiraled into 0 radius. How long would that take? See, as we're going to see here, the early scientists who were only doing classical physics are going to be dumbfounded. They're going to look at this and come up with an answer that not only does the electron spiral in until you have nothing, you don't have an atom anymore, I shouldn't say nothing, but you lose the atom and the electron, hooks and sticks to the proton, and whatever happens then. But the point is, the time is incredibly short. I mean, if at least this was a long time for it to spiral in, you might have some justification for it and say, well, the universe hasn't been around long enough, and so the atom is unstable. But as we're going to see, this is just a small fraction of a second. I think will come up to be like a billionth of a second. And so atoms should not exist for a billionth of a second. And so that's why I wanted to run through these numbers. According to classical physics, atoms can only exist once you if they start at this radius, they would spiral in, they would then disappear within a billionth of a second. And we know that doesn't happen. So we know there's something incomplete about our classical physics. And so that's our fifth reason for our quantum mechanics, or black body radiation, our photoelectric effect, our Compton effect, the sharp spectral lines, and the stability of the atom are all reasons that cannot be explained without the introduction of quantum mechanics. And so that's our empirical science. So if you hear nothing else, that was really the main point of all of this. And you can stop the video here. I just wanted this to go through and do a calculation. In fact, you can just jump to B and put a number in here and get a calculation. You don't have to necessarily prove the equation. Now, to actually prove the equation, we have to do some mathematics here. And I'll start with this. And so the problem says, given this, prove this. Okay. So that's what I will do. But I think kind of a back step to what this equation is actually saying makes sense. And this is why it would not be a good homework or a good test question for you, because this is saying the energy given off depends upon, and some of these terms, these all come from the electromagnetic. So in our case, they come from our chapters 23 through 34, and half of you haven't gone through Physics 122. Those of you who did will know that this E is the charge of the electron. This is the permeability of free space. All of you would recognize the speed of light. And this is the acceleration of the charged particle. And this is the energy it radiates per time. In fact, the equation itself is even beyond the scope of this class. If we had a chapter, a next chapter, and so we ended Physics 121 in chapter 34, but if we had like a chapter 35, we might get into the energy radiated by moving charges. And we didn't do that. So let me make it very clear. None of you who've gone through this class should be even exposed to this equation. So I'm sure that's why the author is saying, look, we did not do this anywhere in the book. He's just saying, according to classical physics, a charge E moving with an acceleration A radiates energy at this rate. And so he just gives it to you. He doesn't expect you necessarily to derive it or expect you have seen it before. And so that's where, like I said, it's kind of a tough problem, because we're just gonna have to take that as given. We didn't do any radiation given from, like, say, an antenna, or in this case a circulating charge around an atom. All right, so let's start this problem here. Let's start the problem with this equation, and then it says show that the radius would change here. All right, so I'm going to begin the problem and eventually hopefully get to this really, really short time frame of how long the atom will last by saying, all right, so here we are, chapter 42, number 3, and say, all right, let's start with this equation. But I'm going to change it a little bit. I'm going to use the chain rule and write the dE dt. But I am then going to put a dr and a dr here. And so how does the energy change with radius, and then how does the radius change with time? Because this is the piece that we're asked to actually get, okay? But starting with dE dt. So I will just put a minus 1 over 6 pi epsilon naught, electron charge squared, acceleration squared, and speed of light cubed. Okay, so again, that's no proof there. We're just given. Okay, so there's my equation here. Now, let me kind of point out that the acceleration would be AV squared over R, as this thing kind of zips around here. Okay, And let me just put the equal sign right here. I'll go dr dt. That's what I'm looking for. Let me leave this alone for just a second. Let me just come over here and go minus. I'm going to put just the e squared, and I will do the 6 pi epsilon naught c cubed. Okay, so I have everything but the acceleration. And then so this should be the acceleration squared. So this would be v to the 4th over r squared. Okay, and then, well, let me just carry this down. d dr. I'll keep working on that. But where I thought I would go with this is not to re-derive all the great work done by your author here. Let me just grab the book from chapter 42, where, again, your author does things like what is the kinetic energy and potential energy. But somewhere in here, your author has the velocity. Right there. So the author has worked out v squared. Okay. So let me just copy that down. So he writes it as Coulomb's constant times the electric charge squared over the mass of the electron over the radius. Okay. So that is the square of the velocity. I guess it's equation 42.8. You can go back if you want to kind of look where he derives that. But he does see, you can see it right here. He sets the centripetal force equal to the electrical force. And again, unless you went through Physics 122, that's electrical force may not make sense to you yet. Okay, but that's velocity squared. So let me make sure I square that since I have velocity to the 4th power. Okay, so minus, and if you look here, this would be an e squared squared, so that's 4, and then 2 more make e to the 6th power there, and Coulomb's constant squared. So that's the numerator. And in the denominator, I guess I have my 6, my pi, my epsilon naught, my c cubed, and then this would be my r squared. Oh, and m squared. Oops, almost overlooked that. So there'd be an m squared and an r squared right here. Okay. Now, the other thing I want to work with is how does the energy change with radius? And again, maybe without working too hard at it, it's actually the next set of equation. There the author has the total energy. It's a negative, and it's Coulomb's constant, and it's charge squared, and it's over 2r. So there would be the energy, and I want to take the derivative of that with respect to r. So let me write everything but the r for just a second. So that would be a, let's see, a negative Coulomb's constant, charge of the electron squared over 2. So let me bring it back into the screen here. Okay, so there's the constants. And then I have the derivative of 1 over r, which you can think of it as r to the negative 1 power. So when you take the derivative, you get a negative 1 and then an r squared. Okay, so that would be how the energy changes with radius. And again, I'm trying to get this. How does the radius change with time? Okay, well, I suppose for starters, I can see 2 negatives, so those go away. I guess I have an e squared, but an e to the 6th. So let me cross out the e squared and change the 6 to a 4. Same here, I have a Coulomb's constant. I've got 2 of them over here, so let me just cross that out and put a 1. And my apologies. And I'm glad I see it now. I was getting nervous. I have an R on each side, but I missed it right here. I was just trying to do too much in one step. Let's come back to this. See, when I did v squared over r, I would have v squared over r squared. And so this right here was all v squared. Coulomb's constant, charge squared, okay. But what I forgot to do is there still is a 1 over r squared from that right there. So the v, this right here is v squared. So I squared it, and then I still got that 1 over r. So this r becomes squared, and that actually should have this to a 4th power. So now, when I look at the r's on each side, I can take off 2 from over here, and I'm down to r squared. Okay. Okay, I like that better. And then that almost takes care of everything on the left. I can bring a 2 or cancel off a 2 with this 6 and be left with a 3. So it looks like what I have is dr dt equals, and let's see, what I'm left with in the numerator is minus e to the 4th, Coulomb's constant, 3 pi epsilon naught, speed of light cubed. And let me put this order back so the constants are all together, and then the radius squared. And so this is the variable, the radius. How does the radius change with time? Now, I don't think I quite have their form yet. Yeah, see, I'm close, but if you'll notice, they don't have a Coulomb's constant because, and again, this is where it would be an unfair question for those of you who haven't gone through Physics 122 yet. But Coulomb's constant can be written in terms of the permeability of free space. So Coulomb's constant is 1 over 4 pi epsilon naught. So let me cancel off Coulomb's constant and replace it with what it's equal to, which is 1 over 4 pi epsilon naught. So that in the top, you just have the minus e to the 4th power. See, that's what they have. There's the minus, and there's e to the 4th power. And then downstairs, we'd have the 3 and the 4, which would make a 12. And then there's 2 pi's multiplied together, so we've got pi squared. And there's 2 permeability of free spaces multiplied together. Then there's the speed of light cubed, the mass squared, and then what changes is our radius as it spirals inward. And so I think we finally got what we're looking for here, and that is what is the rate at which the radius changes. And that does match then what we were asked to. There's the negative, there's the e to the 4th, there's the 12 pi squared epsilon naught, there's the r squared, there's the mass squared, and there's the speed of light cubed. Now, it's probably worth taking a moment, since what I really wanted you to show in this video is how the atom is unstable. And so what this really says is, notice the minus sign, okay? And so that means there is a decrease of the radius with time. So the first thing to notice is to say, all right, according to classical physics, this is saying here that the radius would decrease with time. And it would depend on a lot of factors, including the radius. So at some moment, it has some radius. Let's say that's what they're going to ask us in part B, the 2 times 10 to the minus 10th meters, so 2 angstroms. Okay, and so, okay, there's my radius. But if I put all that in, what does it say? It says it would decrease. And so a moment later, it would have spiraled in a little bit. It would have a smaller radius as I try to read the math here. Now, of course, the smaller radius means this number is smaller. And since it's in the denominator, when the radius gets smaller, this overall piece gets bigger. And so that means the radius decays even more, and then even more, and then even more, and even more, and even more, and spirals in. And it's constantly just getting a smaller and smaller radius. So this is what is meant from the math according to classical physics. According to classical physics, the atom should be unstable. But we know that's not true. So there must be something more going on. And again, this is probably the main point of me just doing the video. It wasn't so much in this math or the derivation, but it was to show you that from classical physics, the atom should be unstable. We know that's not true. There must be something more, and that's why we have quantum mechanics. So the world is something different. Without quantum mechanics, I guess we'd have no world, because all the atoms would spiral in and decay. So it's a good thing we have quantum mechanics, even if it is complicated. But classical physics just doesn't make a stable universe. All right, now the other question to this is, even if it was unstable classically, if it was a long time, especially if longer than the 13.8 billion years of the age of the universe, it still could be acceptable that it spirals in. It's just taken so long. But as you'll see, it's really not that long of a time frame. Because in part B here, it says then, find the time interval for which the electron reaches R equals to 0 when it starts at 2 angstroms. And as I said earlier, you'll see this is not a very long period of time. So I'm going to rewrite this for part B as dr dt equals negative. And now that we just derived this equation, let me write it as some number times 1 over r squared, where that some number would be all of these. And so let me put in a number just to keep me from having to write all this over and over again. So there's the negative, there's the 1 over r squared. What is that number? All right, so I'm going to grab my calculator here and say, all right, let's give it a try. So in the numerator, I have the charge of the electron squared, 1.602 times 10 to the negative 19, and, not squared, to the 4th power, to the 4th power, okay? And then that number is divided by 12. It's also divided by a pi squared. It's also divided by the permittivity of free space squared. That's the 8.85 times 10 to the negative 12 squared for those of you who have not gone through Physics 122, or maybe did and have forgotten that number. Also divided by the speed of light cubed, 3 times 10 to the 8th raised to a power of 3. It's also divided by the mass of this electron squared, 9.11 times 10 to the negative 31 squared. And so I get a number of about 3.18 times 10 to the negative 21. And so here is my equation for the rate at which the radius changes. So it changes according to where it is. And of course, then we are asked to then solve this for how much time it takes. So we have a differential equation. And fortunately, we have a separable differential equation. So let's put all the r's on one side. So r squared dr. And all the time factors on the other. So the only time factor we have is dt. And we can put the constant to either side, wouldn't matter, but leave it up there in the numerator. Okay, and so once we have it separable, we can just integrate both sides. All right, so in this case, I'm going to say let's start at a radius of r naught and continue until you get to a radius of 0. And starting at r naught, I will call it time equals to 0, and it will continue to go until it gets to a time of, I guess I'll call it capital T, although that almost looks like a period, and I didn't want to use a capital T, but I don't have a better one, so this is the maybe I'll call it L for the lifetime of the atom. How long is this atom going to live? Maybe that's a better one. Although that kind of looks like angular momentum. Well, anyways, we're going to call it lifetime. Okay, so this side of the equation is pretty easy. This is just an r cubed over 3 evaluated from r naught to 0, which I guess would be a negative r, because it'd be, well, I should have put the 0 first. 0 minus r naught cubed over 3. So that's the left-hand side of the equation. The right-hand side of the equation is even easier. Minus 3.18 times 10 to the negative 21. And then when you integrate just dt, you get t evaluated from 0 to the lifetime of the atom. And so this would be a minus 3.18 times 10 to the negative 21, and then lifetime. And of course, then notice the two negatives cancel off. That's good. And now we can solve for lifetime. How long is the lifetime? So let's take the radius and cube it. Let's see. So the starting radius was 2 times 10 to the negative 10 and negative 2 times 10 to the negative 10 cubed, okay, then divided by 3. Let's try that again, divided by 3. Okay, so that is the left-hand side of the equation. I'll just hit enter. And then let me divide that by 3.18 times 10 to the negative 21. And this gives me a lifetime of about 8.4 times 10 to the minus 10 seconds, which if you roughly call that a 10, that is 10 to the minus 9 seconds. That is 1 nanosecond for the lifetime. So again, not a good problem necessarily for a test, not even a good one for homework. But a fun one to talk about, at least for me, taking me back to a little bit of classical physics, and maybe for you, showing you the need of quantum mechanics as we're talking about our introduction, even if these equations are a little beyond this one in particular, beyond the scope of this book. And I guess that's why they gave it to you and they only rated it as a medium problem. If they made you derive this, it would be like a really hard magenta to 1. You guys could do it if you've been through Physics 122, but it's something we haven't done. All right. Hope you enjoyed that. Bye.